So yesterday we were working on acceleration, and we're going to pick up right where we left off. Okay, we had gotten through all but two of the formulas that we had listed there. Okay, so we're going to go through those last two formulas. Then we're going to spend some time working on some acceleration problem solving. Okay, just to kind of get the hang of how to use all these formulas, when to use each one, all that kind of important stuff. All right, so what I want you to do right now is write down this example, because this will be the example for our next formula. I'll give you a minute on that one. All right, let's have a look at this question here. So we have a speedboat that is slowing down at a rate of 5 meters per second squared. So what did they just tell me there? Okay, they told me the acceleration, and because it's slowing down, it's negative, okay? Because it's got to go less and less. So negative 5.0 meters per second squared, okay? And comes to a stop. What did they just tell me there?
Final velocity.
And it's 0, right? If the process takes 15 seconds, so that's my time, find the displacement of the boat. All right, which formula am I going to use there? Looking for D, I've got acceleration, final velocity, and time.
Displacement equals acceleration times time. No, distance. D or not. D equals VF minus or VF times time.
Yep.
Minus 1/2 acceleration time. So
Exactly. This is the one we're going to be using here, because we have VF, we have time, we have acceleration. We're looking for D. Okay. Now this one sort of saves us a little bit of work in that, because VF is 0. What's VF times T? 0. Now in the other formula, when that happened, I just got rid of it all. But I'm subtracting. I actually need to keep the 0 there. Adding 0 doesn't do anything. But when you're subtracting something from 0, that makes a difference, because that's going to get us into the negatives. Right? So I don't have to actually manipulate this. I just need to plug in my numbers. So I'm going to have 0 minus 1/2 times negative 5. And that's important, because even though we're slowing down, we're still moving forwards. This negative and this negative are going to make this number positive, which is good, because then my displacement comes out positive. George, question? Yes. Okay, and then times time. The time was 15 seconds, and that's got to be squared. All right, so when we do that, and so, no, I don't want that. Oh, now how do I get back to the other version? You. Oh God, it's getting worse.
Calculator drop down.
Where do you see that?
Up top, right there.
No, I already did that. I need to get rid of the whole big thing. Okay, now back to that. Don't mess up. Come over here.
Thanks for helping.
Okay, so we got 0 minus 1/2, so 0.5 times negative 5 times 15 squared. All right, so we're looking at 562.5 meters, okay, but we only have 2 significant digits, so we're going to have forward or positive. Doesn't really say a direction on there, so I'm going to go with forward, because boats generally travel in a forward direction. All right, let's look at some manipulations, possible manipulations of this formula here. What if I wanted to solve for VF? What would I move first? Exactly, the negative 1/2 AT squared, and I would do that by adding it to the other side, right? So I'm going to have D plus 1/2 AT squared equals VF times T. How do I get VF by itself? divide by t. Remember, that t does not cancel this one, okay, because there's an addition subtraction operation on top. There's my formula for VF. Okay, if I wanted to solve for A, what should I do? What should I move first? Yeah, you can move the VFT. So I'm going to go D minus VF times T. That's going to equal negative 1/2 AT squared. Okay, I have to keep that negative there. Now I want to get A by itself, and I want to get rid of that negative. So what I do generally is I just go, I divide both sides by negative 1/2 T squared, and it just comes over here. Right? Now I'm solving for A. Okay. The other way to do that would be to add AT squared over and do all that. It's a lot more work to do it that way. All right, and once again, you would not have to solve for T unless VF was 0, okay? Because then the T would disappear, the first T anyway would disappear, and you'd have 0 minus AT squared, okay? And you could go from there. All right. Questions on that formula? All right, try these two. They both involve that one. Be on the lookout here. You got that kilometers per hour thing going on. Okay, you got to remember to convert, divide by 3.6. Right, give you a few minutes on those. Okay, so we got the arresting device on an aircraft carrier. I don't know if anyone's ever seen what it looks like when a plane lands on an aircraft carrier, but they got cables strewn across the deck, okay? And there's a little tail hook on the back of the plane, okay? When the plane hits the deck, I mean, an aircraft carrier is not long enough to like slow a plane down by conventional means, like a passenger aircraft would slow down, okay? So they hit these arresting cables, and these arresting cables are tied to these big resistance things that are down in the underbelly of the ship, okay? And they jerk them forcefully to a stop. Okay, like if they ever get a close-up of the pilots inside, it's like, and their head just like snaps forward really hard. Okay, it's like almost being in a car crash every time these kids. There probably has to be a chiropractor on board. Okay, for these guys because they get jerked around really bad when they stop. Okay, 15 meters per second squared is the acceleration. To give you an idea, gravity is 9.81. All right, so this is like 1.5 G's. Okay, to stop you. So the force they feel against their like harness and stuff like that would be 1.5 times their normal weight. Right? So imagine somebody 1.5 times heavier than you standing on your chest. Okay, that's what they would feel when the arresting cable stops them. Okay, so it's pretty forceful. Now, these are people who are trained to endure 6 Gs for certain amounts of time when they're turning in a dogfight or things like that. Okay, they can endure more than that for short periods of time without blacking out. If they go longer than that, then they black out, and then the plane crash is not bad. Okay, but this is kind of instant, right? So we know that the displacement in this one is 150 meters. That's forward, obviously. Okay, they're slowing down, so the acceleration is negative 15 meters per second squared. And we want to find the time it takes for the plane to come to a stop. So what's VF? 0, which is the only situation in which we can solve for time. Okay? So here's what we've got. D equals VF times T minus 1/2 AT squared. So what I'm going to do is say, all right, VF times T is 0. And I'm going to get rid of it, but I'm going to leave the negative. Okay, everyone all right with that? All right, so now I'm going to try and isolate T. So what do I have to do with the negative 1/2 times A? All those three things are being multiplied together. How do I move the half and A? All right, divide both sides by negative 1/2 of A. Boom, those are gone. That solves for T squared. What do I want to find? I want to find the square root of that because I'm looking for T, not T squared. All right, so now I've got my formula. All I have to do is plug in my numbers. So t will equal the square root of 150 divided by negative 1/2 times negative 15. And here's where the signage is important. If you don't carry those signs over and you plug that into your calculator, it'll have a conniption fit. Okay? It will say, you can't do that, because you can't take the square root of a negative number. Right? Having the negative 1/2 and the negative 15 will make that come out positive, and then my calculator will be happier with me and will actually work. All right, so we got square root of 150 divided by this, negative 0.5 times negative 15. All right, so that's going to take us 4.5 seconds. Right, which is exactly what they got here. So we did okay. For question number 2, right, we've got the 1968 Corvette took 6.2 seconds to accelerate to 100 miles an hour. 160 kilometers an hour is exactly 100 miles an hour. Okay, they did that in 6.2 seconds, which was impressive. 327, that's very powerful. All right, so t equals 6.2 seconds. We need to calculate VF, okay, by dividing the 160 kilometers per hour by 3.6. So we're looking at 44.4 meters per second, and it traveled 220 meters north. Okay, so find the acceleration. So again, I'm going to be using this formula because it's the only one that has everything not equals, minus. Okay, so I'm solving for A. So I would first move the VFT over by subtracting. And then I'm going to divide both sides by negative 1/2 of times t squared. And that'll leave me with my formula for A. And now I can plug in my numbers. Okay, so that's going to be that A will equal 220 minus 44.4 times 6.2 divided by negative 1/2 times 6.2 squared. Right. So, so I've got a negative number on the top, and that's okay because I'm going to get a negative number on the bottom as well. Okay, divided by negative 0.5 times 6.2 squared. Okay, so the acceleration is going to be 2.9 meters per second squared, north. Okay. So a bit of a tricky manipulation. Sorry, Ty, did you need to see the calculator again? You looked really disappointed on the finger.
Why would you minus the VFT when you're subtracting it from the 1/2 AT squared?
I'm not subtracting the VFT from the 1/2 AT squared. I'm subtracting the 1/2 AT squared from VFT. VFT is positive.
Okay.
That's why I have to subtract it. Yeah. All right. Everybody okay with that? Okay, you got one more acceleration formula to go over. And it's actually pretty easy. There's just lots of squares in it. 2 of the things are squared. So you do a bit of square rooting when you use it. All right, so I want you to write down this example right here. I'll make it a little bit bigger so it's easier to read. Okay, then we'll go over it. Okay, so and this question is kind of one of the examples of where Hollywood very often misrepresents what happens in real life. Okay? If you ever watched any action movies, okay, where there's any gunplay of any kind, everybody always hears the sound of the gun, and then the bullet goes whizzing by them or hits them or whatever. Okay? What we're going to calculate here is the velocity at which a bullet leaves the barrel of a gun. And that's going to tell us something about the situation that Hollywood often portrays about hearing the sound of the shot before the bullet. Okay? So what we have right now is that we know the distance the bullet is going to accelerate. It's 0.750 meters. Okay? We know the acceleration of the bullet, and it's massive. Okay? I mean, a bullet is going really fast when it leaves the barrel of a gun, and a barrel of a gun is not very long, right? So it doesn't take very long for the bullet to get out, which means it has to be accelerating at a huge amount. Okay? 5.35 times 10 to the 5 meters per second. That is a huge rate of acceleration. Okay, what was the, we kind of have to read into the question here, but what's the initial velocity of a bullet in a gun? Zero. Okay? And we're not saying the person was running when they fired. Okay? We'll assume that the person was stationary because, well, you know, that's another action movie thing where being hyper accurate while running. Okay? It's a bit unrealistic. Okay. All right, so we're looking for VF. So the formula that I have to use is the only one we haven't used yet, and it's this one. VF squared equals VI squared plus 2AD. Okay. In this case, I don't need to manipulate because I'm already set up to solve for VF. That's actually not true. I need to do one thing. What is it? This solves for VF squared, and I just want VF, so I need to square root. Right, so VF will equal the square root of 0 squared, which is 0. I wouldn't even necessarily have to write that. Okay, plus 2 times 5.35 times 10 to the 5 times 0.75. Okay, so in my calculator, square root of 2 times, in brackets, 5.35 E5 8 times 0.75. Okay, so the final velocity of the bullet leaving the gun is 896 meters per second. Is that fast? Very fast. How fast does sound travel? Not as fast. 1/3 approximately as fast as this. Okay, speed of sound at 20 degrees Celsius, 340 meters per second. And if you've ever been to a track meet, this becomes very obvious. If you're at the finish line and the starter fires the pistol, you see smoke and then you hear the sound of the shot. Well, unfortunately, it is the same for someone being shot at. Soldiers have a saying, you never hear the bullet. Because you don't. You don't hear the bullet that kills you. Because it's traveling faster than the sound of it being fired. That's scary. Okay? And you can actually see this. They've got footage, okay, of like snipers in like Afghanistan and places like that where they were doing the peacekeeping missions, which incidentally, like if you've seen American Sniper, read the book or seen the movie, they actually do a good job portraying it there, where the people being shot at, if it's a miss, react very differently than people who would hear the sound of a gunshot, right? So if there's a miss, you see like a puff of dirt where the bullet strikes the ground. And so what you typically see is people looking down, and then like a second and a half, or in some cases. 3 seconds later, you see them do this. And they turn, because then the sound finally gets there. Okay? Meanwhile, if the sniper's any good, first off, he wouldn't miss. And secondly, would have a chance to probably fire 1 or 2 more times before the sound of his first shot would reach. Okay? The longest sniper shot is held by a Canadian, and it's just under 4 kilometers. Okay? That's not somebody you want to be on their bad side. Okay? 4 kilometers away. You can't even really see 4 kilometers if you look out the window. Okay? That's a long, long way. And somebody was able to hit, unfortunately, a person, okay, from that distance. Okay? Well, I mean, it's still a person dying. It's impressive, but it's still somebody being killed. Okay? It's impressive in that, oh my God, somebody could shoot at me and hit me, and I wouldn't even know they're so far away. Scary. Okay? What's that?
Isn't that impressive?
Okay, so that's pretty fast, but that is one of those things that Hollywood doesn't always do a good job of representing, because they always, you see people running and dodging bullets, and you can hear the sound, and it's just unrealistic. Okay, and high-powered sniper rifles are going to fire the bullets even faster than that. Okay, so yeah, it's pretty crazy. But a shot that long, when we start talking about projectile motion, there's a lot that goes into that. That's not just somebody who like, all right, and looks down the scope, pulls the trigger. Okay, there's a lot of, okay, they've got somebody telling them about the wind. Okay, they've got somebody telling them about the drop, because as soon as the bullet leaves the barrel of the gun, gravity starts acting on it, and it starts to fall. So they actually have to aim way above their target and correct for any wind. And if the shot is over, let's say, 1.5 kilometers or so, they have to take into account the Coriolis Effect. That is the rotation of the earth under the bullet as it flies. So this is no small feat, okay, of marksmanship to hit a target that far away, right? And it's not luck, right? Nobody hits that shot by luck. In fact, that sniper has several of the long range records, like broken his own record.
Can we watch it?
No, I don't have the video of it.
The guy who landed it said it took them like 10 minutes to set up the
To
shot.
set up the shot, yeah.
Like, cause he has all of his guys helping beside him, with their binoculars and everything, and they're like taking into account everything, and it was like.
Yeah, it was pretty crazy. And when you watch like American Sniper, you see that, like, he's always got he's got a spotter, unless he's talking short range shots, which are still impressive, but when he's talking about the really long range ones, you don't do that by yourself. You're getting windage, you're getting range, you're getting drop, you're getting velocity if you're shooting at a moving target. Okay, stuff like that. So, yeah, but it's all physics. Physics is good. All right, I want you guys, oh sorry, let's look at manipulations. We didn't look at manipulations of this formula. So, for this formula, so I got VF squared equals VI squared plus 2AD. This one's quite a bit easier to manipulate than the others. If I want to solve for VI, what do I do? Yeah, subtract the 2AD. So I'll have VF squared minus 2AD, and I'll have to square root that, okay, in order to get VI. That'll give me VI. Right? Now, sometimes I see people do and it's wrong. They put the square root over and they take the square off the VF. That's not right, okay? It's the square root of everything underneath there. So VF still has to be squared, added to 2AD, or subtracted, sorry, minus 2AD, and then square root everything. All right, if I want to solve for acceleration, then I'm going to subtract VI squared, so I'll have VF squared minus VI squared equals 2AD, and then if I want to solve for either A or D, I just divide the other two parts over. So if I'm solving for A, I would divide both sides by 2D. If I was solving for D, divide both sides by 2A. A little easier manipulation than that. Yes, you can. All right, try these two here. Make it a little bit bigger. You may not, on some of these you can actually use some other formulas. So look at what you're given, okay? You may not necessarily have to use the formula we just went over, right? So you can pick something else if it applies. Give you a few minutes on those and then we'll walk through them together. Okay, let's have a look at number 1, and I'll give you a little bit more time to work on number 2. Okay, so in number 1, we have a jetliner that lands on a runway at 70 meters per second. Okay, so VI is 70 meters per second. It reverses its engines to provide braking, which is exactly what they do. I don't know if you've ever been on a plane. Okay, when they land, you suddenly hear the engines get really, really loud, okay, and the plane starts to slow down really fast. Okay, 'cause they actually reverse the engines and they pop up these big flaps. Okay, that provide a bunch of air resistance. Okay, and they come to a stop, so VF equals 0 meters per second, 29 seconds later. Okay, what's the jet's acceleration? Okay, so what formula would I use here? What would be my best choice?
A equals VF minus VI.
Exactly, that first one that we learned in Science 10. Change in velocity divided by change in time is the easiest one. I don't even have to manipulate it. Okay, it would just be 0 minus 70 over 29 seconds, right? And that'll give us our negative 2.4 meters per second squared. Okay, or 2.4 meters per second squared backwards. Okay, would probably be more accurate because it does, actually it never says forward anywhere on here. Okay, what length of runway did the jet require to come safely to a complete stop? Well, at this point I have VI, VF, T, and A. I can use any formula I want that has D in it, okay, at this point, and I'll get the right answer. For me, I like to use one that maybe has numbers I was given in the question as opposed to numbers I calculated, but I can't do that because I calculated A, and A is in every other formula that we have. Right, so I'm going to go with one that I don't have to manipulate. Okay, I'll go with that one just because I have all of that stuff and it's set up to calculate D, so I don't have to do any extra math. Okay, so VI was 70 times 29 plus 1/2 times negative 2.4 times 29 squared, and that should give us 1.0 kilometers. Because we only have 2 significant digits, or 1.0 times 10 to the 3 meters would work as well. Okay, it doesn't, I mean, you have to round it here, but. So it comes out to 1,020 meters, but with only 2 significant digits, it's 1.0 times 10 to the 3. Are you right with that?
I don't understand
What do you mean?
how the 1,020.8 could be the 10 to the 3.
Well, because I can only keep these 2 digits here, the 1 and the 0, right? And 2 won't round the 0 up. Right? So when I'm moving the decimal to put it in scientific notation, okay, I move it to here, 1, 2, 3 spaces, right? 10 to the power of 3 is 1,000. 1 times 10 to the 3 is just scientific notation. Yeah. I'm just representing this number with the correct accuracy given the numbers I was given. I can't show all that because I can't be certain of anything past this digit, given the stuff I was told. Okay, how many people are done number 2? Are we stuck on number 2?
No.
We just need a little bit more time? Okay, I'll give you a couple more minutes. Okay, so let's have a look at question number 2 here. So, on-ramps, which are used to merge from an overpass onto a freeway, okay, are designed so that you can reach the speed of the highway as seamlessly as possible. Don't be like so many people who don't know how to do that. It drives me insane when I'm trying to merge and the person in front of me is going 75 and going over into traffic going 120. That's how you die, okay? When you merge, accelerate. It's the pedal on the right. Okay? If you depress that down, the car goes faster. Okay? And you can reach the same speed as the vehicles on the highway no matter how gutless the car you drive. Because, well, on-ramps are designed for that. They're downhill. Gravity helps. Okay? That. Just that's my rant. Rant over. Okay. So we've got VI and we've got VF, but they gave them to us in kilometers per hour, so we need to convert them first into meters per second. Okay, so 100 divided by 3.6 is going to be our 27.7. Oh, sorry, that's VF. 27.7 meters per second, and then our VI would be half of that. Okay, 50 divided by 3.6. So 13.8 repeating meters per second, and the acceleration is 3.8 meters per second squared. And that's another thing. When they're designing these on-ramps, they essentially take into account what would essentially be the slowest vehicle that would have to use it, and they have to make it, essentially long enough for, that big B-train semi-truck, okay, to get up to speed before it would merge over. Right? So we are looking for the minimum length of the on-ramp. This one will require us to use this formula. And we're trying to solve for D. So the first thing we want to do is bring the VI over. And then we're going to divide both sides by 2A. Okay, that will leave us with D. Okay, and then we just have to plug in our numbers. So VF squared, sorry, we put in the numbers here. So 27.7 squared minus 13.8 squared divided by 2 times 3.8, right? And that should give us our 76 meter long on-ramp. Okay, so tomorrow we'll be working on acceleration stuff, and we'll be doing a lab. I think I have a book for Thursday, unless I have a book for tomorrow, to double check. But we will be doing a lab on acceleration either tomorrow or Thursday. Okay, working on acceleration the other day, and then we'll be starting vector addition the day after that. Okay, so we're moving right along. Thursday's quiz, incidentally, will be on acceleration. All right, we'll call it a day there, guys.